This is Mark Kelly of The Roots, welcoming you to another math tutorial video by Mr. Witt and Fort Bend Tutoring. FBT, where personalized math tutoring is the solution.
Hello, ladies and gentlemen. This is Mr. Witt with Fort Bend Tutoring, and today's lesson is going to be about imaginary and complex numbers. So, what are imaginary numbers, ladies and gentlemen? Well, just like you, mathematicians got tired of not being able to take the square root of a negative value. So they came up with this imaginary number I and said that that would be equal to the square root of -1. So not only did they come up with this imaginary number, they also came up with a sequence for that number as well. And they said that I to the first power would equal to I to the second power equals to -1, I to the third power equals to -I, and finally I to the fourth power equals to 1. The sequence continues in that order. All right, so it just starts over with I to the fifth power equaling to I again, and I to the sixth power equaling to -1, so forth and so on. All right, now we have examples for you. Let's check out example 1A in simplifying these imaginary numbers. Since I showed you that the first 4 i's in this sequence will repeat, all we have to do when simplifying an imaginary value is divide it by 4. So for instance, here I have I to the 14th power. I can simplify this by dividing by 4. So 4 goes into 14, let's see, 3 times, and that gives me a 12, and it gives me a remainder of 2. It's this remainder that we'll use to convert I to the 14th power into I to the second power. And remember, I squared is equivalent to -1. So this answer here is -1. Done. And that's it. Let's go ahead and put a red box around that. So this answer, I to the 14th power, is the same thing as I squared, which is -1. From there, let's look at our next example. In 1b, I have I to the 12th power. So with this I to the 12th power, I'll once again divide by 4. 4 goes into 12 3 times to leave me with 12 and a remainder of 0. Okay, so we'll use this remainder of 0 to rewrite our original expression as I to the 0 power. And remember, anything to the 0 power other than 0 is 1. So that's our answer, 1. Let's go ahead and put a box around that as well. Okay, here we are. Continuing on, we have 1c. This is I to the 39th power. I'm going to start out by dividing by 4 due to the sequence that was given above. So I'll have 4 going into 39. That goes in there 9 times. That'll be 36, and that gives me a remainder of 3. I'll use the remainder of 3 to rewrite our original expression into I to the third power. And according to the table above, let me show you. This table right here, I to the third power equals to -I. So that'll be our answer. So since our result was I cubed using the remainder, we'll end up with -I as our result. Done and done. Let's go ahead and put another red box around that. All right. Well, with 1d, we have I to the -1st power. And when you have a negative exponent, remember that base will be brought into the denominator. So I'll be rewriting this as 1 over I. So just like with your radicals, you're not going to leave an imaginary number in the denominator. So we'll be rationalizing that. When you need to rationalize an imaginary monomial, one term with an imaginary value in it, all you need to do is multiply by I over I, okay? So the form of 1 that we'll use to rationalize this is I over I. From there, we'll multiply straight across, and 1 times I is I, and I times I is I squared. Remember that I squared equals to -1, so that means that I divided by -1 is going to be -I, which is our answer here. And this is the result. So once again, you will not leave an imaginary number in the denominator, and we did that to get rid of our negative exponent. From there, we rationalize by I over I, that form of 1. That's the version of 1 that we chose to rationalize it. And then we end up with I over I squared. Remember that I squared, according to the table above, is -1, and I divided by -1 is -I, which is your answer. So those are our initial problems for our imaginary numbers and complex numbers. Speaking of which, when it comes to complex numbers, we'll be looking at this format. When you have complex numbers, that means a combination of real numbers and imaginary numbers. The first value must always be your real number, and then the imaginary part will always be last. So we'll write it in the format of a plus bi. That's the standard form of a complex number. So let's take a look at our 2a right here, problem number 2a. Here I have the square root of -64. Normally, this would be undefined, but since we're using imaginary numbers today, I'll rewrite our square root of negative 64 as the square root of 64I squared, remembering that I squared is equivalent to negative 1. So that's where that negative went in our original expression. I converted that negative 1 into I squared. From here, we can go ahead and simplify the square root. So the square root of 64 is 8, and the square root of I squared will be I, and that'll be your answer, 8I. Just like that. All right? 2b. We have the opposite or negative square root of negative 36. So what I'll do here is I'll rewrite this as a negative square root of 36I squared. Once I have it rewritten this way, I can go ahead and bring down that negative sign, and the square root of 36I squared will just be 6I. So that gives me an answer of negative 6I for 2b. That's right. Let's keep it moving, ladies and gentlemen. Next problem coming up. We have problem 3a with the square root of negative 4 times the square root of negative 9. Now, when dealing with impossibilities such as this, where we have the square root of negative 4 times the square root of negative 9, you will not simply multiply what's underneath the radical. See, normally when you have the same index as we do here, these are both square roots, you would just multiply the radicands together. In other words, what's underneath the radical sign. But not when you have imaginary numbers, because remember, these are impossibilities to begin with. So go ahead and rewrite it, showing the reader that, hey, this is an impossibility, so you're going to use an imaginary number. So I'm going to rewrite the square root of negative 4 as 4I squared. All right, times the square root of negative 9, which will now read as the square root of 9I squared. So converting those negatives into I squareds. And you only need to do this when you're simplifying even indexes, such as a square root. Okay, so from there, I'm going to go ahead and take the square root of 4I squared, which is 2I, times the square root of 9I squared, which is 3I, and then I'll be multiplying straight across. So multiplying 2I times 3I, that gives me 6I squared. So remember, I squared equals to negative 1, so we'll rewrite this as 6 times negative 1, and 6 times negative 1 gives us an answer of negative 6, which is our answer here. All right, that does it for 3A. In 3B, we'll be looking at the next problem here, which is the square root of negative 3 times the square root of negative 7. Once again, when you begin with an impossibility like the square root of a negative number, go ahead and rewrite that. So we'll rewrite it as the square root of 3I squared, taking that negative 1 and converting it into I squared, times the square root of 7I squared. So now I'll simplify this by showing that the square root of I squared is I, so that gives me I times the square root of 3, times the square root of I squared is just I, times the square root of 7, and then I'll be multiplying my i's together here, okay, because they're the coefficients. I times I is I squared, so I have I squared times the square root of 3 times 7, which is 21, and remember, I squared is equivalent to negative 1, so this is going to be negative 1 times the square root of 21, and I can just simplify that to negative square root of 21, and done. That's the answer. Here's your red box. Done and done on that one. All right, that was 3B. Let's keep it moving. We got more to show you. Problem number 4 coming your way. With 4a, we have the square root of negative 75 divided by the square root of negative 3. So just like with our multiplication, we have an impossibility going on. We can't take the square root of negative 75. We'll need to use imaginary numbers. So show that you're using the imaginary numbers. So I'm going to rewrite this as the square root of 25 times 3I squared, all right? So I'm recognizing that I have the largest perfect square of 25 within 75, so that's why I broke it up into 25 times 3, and of course our negative value becomes I squared, all right? So that's what I have right there. If you need help simplifying square roots, go ahead and check out our video called Simplifying Square Roots. I'll go ahead and put a link right here at the bottom. All right, in our denominator, we'll rewrite the square root of negative 3 as the square root of 3I squared. All right, from here, we'll go ahead and simplify those square roots further, and we'll say that the square root of 25 is 5, the square root of I squared is I, and that leaves me with the square root of 3. And the denominator, the square root of I squared is I, so that comes on the outside, and that'll be times that same square root of 3 that's left over. Notice that we can simplify this because the I square root of 3's will cancel out. So that'll just leave me a value of 5, and that's it. Here's the red box. All right, so the first thing we did was we took the square root of negative 75 and we broke it down into 25 times 3i squared. Then we broke down the square root of negative 3 into 3i squared, and from there, simplifying, in other words, taking the square root of those perfect squares, we ended up with 5i times the square root of 3 over I times the square root of 3. It's those I square root of 3's that canceled out in the end to give us an answer of 5. All right. 4b, we have the square root of negative 32 divided by the square root of 8. So my first step is going to be to rewrite our expression showing all of my perfect squares that can be simplified. So I'll rewrite this as the square root of 16 times 2i squared over the square root of 4 times 2. So knowing that 16 is the largest perfect square within 32, I rewrote it as 16 times 2. I took that negative value underneath that square root and wrote it as I squared over the square root of 4 times 2 because 4 is the largest perfect square within the number 8. All right, continuing on. We'll have the square root of 16 as 4. The square root of I squared is I. That leaves me with the square root of 2. And in the denominator, I have the square root of 4 being 2 times the square root of 2. And now it's the 2 that can go into the 4 twice. These square root of 2's will cancel out. And so my result here is going to be 2i, and that's the answer. That's it. Box around it. Okay, that's problem 4b, ladies and gentlemen. Now we're going to be moving on to problem number 5. In problem 5a, notice that we have these quantities that we're combining together. We're going to add them. And we'll keep in mind that the standard form of a complex number is a plus bi. A plus bi, the real number before the imaginary number. So all I'm going to do first and foremost, ladies and gentlemen, is just drop the parentheses here. I'll just rewrite it. So this is going to be 4 plus 2i plus 3 minus I minus 6 plus 3i. Okay, so in dropping those parentheses, I just brought all my terms together, got rid of those parentheses because they were distracting, weren't they? All right, so combine all the real numbers first. So I have 4 plus 3, which is 7. 7 minus 6 gives me a positive 1. Then combining the imaginary numbers together, I have 2i minus I, which is I, and then I plus 3i gives me 4i. So my result here is 1 plus 4i, and that's it. That's 5a, ladies and gentlemen. Done and done. Now moving on to problem 5b. With 5b, we have the quantity of 7 minus 3i minus the quantity of 8 minus 6i. So I'm going to drop my parentheses as well as distribute this negative. So I'm going to get my arrows popping. So bringing down this 7 minus 3i, this gives me negative 8 plus 6i. Then combining my like terms, I have 7 minus 8, which is negative 1. Then combining my imaginary numbers, negative 3i plus 6i gives me a positive 3i. And that's going to be the answer to problem 5b. Got a box around it now. All right, so from beginning to end, there we have it, 5b. All right, ladies and gentlemen, let's check out problem number 6. With 6a, we're going to distribute. That's right, my favorite property, about to get those arrows popping. So anytime we have a term outside of a set of parentheses like this, we're going to multiply. So I'll be distributing 4i into the parentheses here. I got my arrows popping there. So you have 4i times 2, that gives me 8i, and then 4i times 3i gives me 12i squared. From here, ladies and gentlemen, we'll go ahead and remember that that I squared value equals to negative 1. So I'll rewrite it as 8i plus 12 times negative 1. Then multiplying, we know that we'll have 8i minus 12, but remember, in standard form, you must write your real number first. So the way you'll submit your answer is as negative 12 plus 8i, and that's it. Red boxing it. Okay, next problem. Problem 6b. Notice here we have a binomial times a binomial. So 2 terms times 2 terms. So that means that you can use the distributive property, aka you can FOIL it. All right, you can use the FOIL method. So remember, we do have a video on multiplying binomials, all right, using the distributive property or the FOIL method. So check that out. So I'm about to get my arrows popping here. So I got my arrows popping and I'll be multiplying this stuff out for you. So starting out, we'll be multiplying 3 times 4, that gives me 12. 3 times negative 2i is negative 6i. 5i times 4 is a positive 20i. And 5i times negative 2i, that gives me a negative 10i squared. Like that. All right. From here, I'll be combining my middle terms together. So rewriting this, I'll have 12 plus 14i, and remember that I squared is equivalent to negative 1. So I'll bring down this negative 10 times negative 1, just like that. Multiplying next, I have 12 plus 14i, and negative 10 times negative 1 is just positive 10, right? Okay. Remember, we'll be writing our real number first, so 12 plus 10 is going to give me 22. And I'll bring down this positive 14i, and that is my answer for problem 6b. Just like that, ladies and gentlemen. Just like that. Let's move on. 7a is in the house, ladies and gentlemen. 7a. With problem 7a, I have 1 plus I divided by I. Remember earlier I said you will not leave your imaginary numbers in the denominators. So we'll need to rationalize this. So we do have a monomial, one term in the denominator that's imaginary. So in those situations, you always multiply by I over I, ladies and gentlemen. Okay? So I'll be distributing that I in the numerator. So we'll start off with 1 times I, which is I, and then I times I gives me I squared. So we end up with I plus I squared after multiplying I times both of these terms in the numerator. Then in the denominator, I times I is I squared. Okay? From here, we'll simplify this knowing that I squared is equivalent to negative 1. So this becomes I minus 1 over negative 1. And anytime we divide by negative 1, ladies and gentlemen, you know that's just going to change the sign, right? So changing the signs of these terms in the numerator, we'll end up with negative I plus 1. All right, and rewriting this in standard form, you know that we have to have our real number first, so it'll be 1 minus I, and then that is our answer, ladies and gentlemen. Done and done for problem 7a. All right, got one last problem for you. All right, thanks for hanging in there with me. In problem 7b, we have 8 plus 9i divided by 5 plus 2i. Anytime you have an imaginary number in the denominator, you'll need to rationalize that. But because we have two terms in the denominator, we'll need to multiply by the conjugate. That's right, the conjugate. So the conjugate of the denominator here is going to be the following. It'll be 5 minus 2i. You simply change the sign on that last term in order to find out the conjugate. And notice that we end up with a binomial times a binomial, not only in the numerators, but also in the denominators. So we'll be using the distributive property, aka foiling these out, in order to get our next step. So here we are. We'll multiply 8 times 5 to give me 40. 8 times negative 2i is going to be negative 16i. 9i times 5 is 45i. 9i times negative 2i gives me negative 18i squared, and all of this is going to be over. Foiling this out in the denominator, we'll have 5 times 5, which is 25. 5 times negative 2i is negative 10i. 2i times 5 is a positive 10i, and 2i times negative 2i gives me negative 4i squared. All right. In our next step, we'll be combining our middle terms together as well as converting those I squareds into negative 1. So here I now have 40. This is going to be plus 29i minus 18 times negative 1. All of this is going to be over 25. Your middle terms here will cancel out in the denominator, and I'll bring down a negative 4 times negative 1. Next, I'll be rewriting this. I'll have 40 plus 29i plus 18 all over 25 plus 4. Okay? In the numerator, we can combine that 40 and 18 together. So 40 plus 18 is always 58 plus 29i, which is going to be over 29. That's the result of that 25 plus 4. Notice that all three elements of our expression here can be reduced by 29. So in other words, I'm just going to take the numerator and divide it by that 29 in the denominator. So it turns out that 29 times 2 is 58. So 58 divided by 29 is 2, plus 29 goes into itself once and leaves me with just I. So the answer is just 2 plus I, ladies and gentlemen. That's it. All right, so that's it for 7B, and that's also it for this lesson for today. So this was Mr. Witt with Fort Bend Tutoring. We were discussing imaginary and complex numbers. As always, please rate, comment, and subscribe. And as always, if you're able, please donate for more free math videos. Peace.
Please rate, comment, and subscribe. Like our Facebook page, Fort Bend Tutoring, and visit us on the web at www.tutormemath.net.